Alright, welcome back to another section of ordinary differential equation, which is what? ODE. Alright, so here we are going to, in this video, by the end of this lesson, you should be able to define initial value problem, explain the theorem of existence, and uniqueness of a solution of first order differential equation, and also show that a given IBP has a unique solution in a given interval or not. And also lastly, you should be able to explain the geometrical interpretation of initial value problem, which is the same as what? IVP. So let's start with initial value problem, which is IVP. When the auxiliary conditions are all specified at more than one, are all specified at more than one point on the interval of interest, the resulting problem is called the IVP. That is all what we are saying. And also, for example, we can also have that this is the function and we have the IVP here. We also have this differential function and the IVP, differential function and it what? IVP. But we also have IVP and we have BVP. BVP is boundary value problem. And that one too is if the auxiliary condition are specified at more than one point. The same thing. The auxiliary condition are specified at more than one point. But let's see what is coming now. At more than one point on the interval of what? Interest. The resulting problem is called a boundary value problem. A boundary value problem, which is BVP. We will be looking at that in a whole in our latter part of the course. Alright, so let's look at theory of existence and uniqueness of solution of first order differential equation. So all that we are saying about this theorem is that if we have a function, if let's say we have a function f and a partial derivative f as respect to what? S. This is a partial derivative of f as respect to y. As respect to y are continuous. So if this and this are what? Continuous. Are continuous function in the same domain. A domain like what we have been given here. In the same what? Domain. Then all that we are saying is that there exists a unique solution of what? The IVP. There exists a unique solution of the IVP. And the IVP can be y prime is equal to f s comma what? Y, and can be given as that. Alright, so that is all what we are saying. Good. So that means that this is defined on some what? Interval. And that interval is, what we are saying is that if this is continuous and the partial derivative of f as respect to y is also continuous, then we say that there exists a solution within this what? Interval. And that interval is s minus s naught. S minus what? S naught. Being less than or equal to what? H. That is that. Where h is sufficiently what? Small. The notation, I would like you to write this. The notation, partial derivative of f as respect to y. The notation this denotes the partial derivative of function f with respect to y, as I said. Now, let's look at some examples and I'll explain it well for you, or the understanding of this will become more clearer when we get into solving of the what? Of the question. So for instance, let's look at this question. Show that, I would like you to write a question. Show that the given IVP has a unique solution in some interval of the form. In some interval of the form. Show that the IVP has unique solution in some interval of the form. Alright, and that IVP is x squared plus y squared. Alright, so let's look at this question. And you will have it. It's not difficult. You will now understand the IVP and all that we are saying here. Alright, so note that here the y prime, don't forget what he states here. He said that the y prime is equal to that. And when you are given y prime to be equal to s squared plus y squared, that is telling us that y prime is equal to fs, comma what? Y. I'll be clear. Alright. And that is s squared plus what? Y squared. So we now check whether this function given us, the differential function given us, is continuous or not. How can we see if it is continuous? To see whether it's continuous is just simple, family. You know that the IVP is given to you, and the IVP you have is that when you plug in 0 into the function of the y, you are going to get what? 0. So this s represents what? 0, and the y here to represent what? 0. So we are going to do the substitution to this. And when you punch on your calculator and you don't get something like math error, it means that it is continuous. You see, no matter when you put in s to be 0 here, you get 0 squared plus what? 0 squared. This will give you 0. You will not get something like what? Math error. There is a case that you can get mass error, and that is not in now. We'll go back, we will move on to another person which is dealing with search. But this is continuous, since you can get a perfect value after the substitution. So here means that you put s to be equal to 0, y to be equal to 0 in this, and we can now say that fs, y is continuous. Is continuous. You can continue on everywhere. It's continuous on everywhere. The second step is that we are going to take the partial derivative of the function as respect to what? Y. The partial derivative of f. This is that. As respect to what? Y. What this means is that we are going to take a partial derivative of f as respect to y by holding s what? Constant. By holding s what? Constant. So if you have f to be equal to s squared plus y, and you are holding this, please write this down. Partial derivative of f as respect to y means that you are taking the derivative of the function as respect to y by holding s constant. So if this, the whole of this is a constant, the derivative of this is 0. So you get 0 plus, and the derivative of this y squared is what? 2y. So we get 2y to be our results. Then after that, you check whether the IVP, where s is equal to 0 and y is equal to 0, is continuous away here. And also here, we know that we don't have any value of what? Take your calculator, we don't have any value of what? X. So it's only y. And when you put in y is equal to 0, we are not going to get anything like mass error on our calculator. We are just going to get a perfect answer. And that answer is what? 0. So we now say that this is continuous. Continuous what? Everywhere. Now, the theory says that if f is continuous and the partial derivative of f as respect to y is also continuous, then we say that the given function is unique. The given function is what? Unique. So looking at what we have here, we can now conclude that since both f and partial derivative of f as respect to y are continuous about the point, that's the conclusion, right? Since the function f and the partial derivative of f as respect to y are continuous about the points, 0, 0, are continuous about the point 0, 0. There exists a positive number. There exists a positive number h, such that the conclusion is very important. The conclusion such that s minus s naught is less than or equal to what? H, where h is sufficiently small. That is all for that. The conclusion is just simple. Since f and the partial derivative of f as respect to y are continuous on the point 0, 0. Where is the point 0, 0 coming from? It's coming from the IVP to be the s is 0, the y is what? 0. Then it means that there exists a positive number in the interval. This is that. Alright, so let's look at another example here and you will have it. Alright, so let's move on. Looking for another example. Oh. Okay, we have one here. We have one example here. We are to verify whether the following differential equation whether the following differential equation in short has a unique solution at 0, 0. Explain, that's the conclusion. Explain why that. And the A is y prime plus 2sy is equal to 0. And we also have B. dy 3y dx is equal to 2s dx. And also have c, which is sy prime plus 1 minus s y is equal to s e raised to power x. Alright. So that is the question that we have under that. So we are going to see how we are going to go about it, and trust me, you will love it. Alright. Okay, verify whether the following differential equation has a unique solution at 0, 0. At 0, 0. Explain why. So the A is like this. Now, always don't forget that it's supposed to be in the form f, s, y is equal to, is equal to y prime, or let's put it well, y prime is equal to f, a function of y prime is always a function in terms of s or what, y, and the initial problem will be that is 0, 0. So s is 0 and y is what, 0. So looking at the first question, we can put it in this way, we can put it in this way, all right. But be careful, we have this to be what, y prime plus 2sy is equal to what? 0. That means that we have to make what, y prime the what? The subject. Before we can, because we are saying that it's a function in terms of s and y. So here y prime is going to be equal to negative 2s what? Y. So we are going to get y prime, sorry, f comma s, which is y prime will be equal to what? 2sy, negative 2sy. Then our condition 2 will come to this side. Our initial condition, that is the initial condition, that will come to that side. I hope it's clear there. So the first thing is that we write f(s), y to be equal to negative 2sy. Now, is this continuous everywhere? Exactly yes, because when you do a substitution of 0 to s and 0 to y, you're not going to get anything like undefined or mass error. You will not get something like that. When you point that, you will not get something like that. So this is continuous everywhere. Then we go for a partial derivative of the f as respect to y by holding s constant. So when we hold s constant here and we take the derivative as respect to y, we are going to get negative 2s, because this the whole of this will be what? A constant. So when we take the derivative as respect to y, this one will go, so we get something like that. And in this one to continuous family, surely it's also what? Continuous. So it's continuous everywhere. Then you conclude that the differential equation is unique. It's unique on the point 0, 0. That means that this differential equation is what? Unique on the point 0, 0. I hope it's clear. Alright, move to the second question. Let's move to the second question. B. Straightforward. Woo! Now we have to do something about it before we can put it in this form. Alright? Before we can put it in this form. We know that 3y here is dy is equal to 2s dx. So we have to put it in a form dy dx is equal to, or y prime is equal to. So here divide here by ds, divide here by ds. So you get dy dx. and we have 3y here to be equal to this. Will take away this, so you get 2s. Hope you can see that. Alright, so therefore y prime 3y prime is equal to what? 2s. And y prime, I hope you can see from here, y prime is equal to 2s over 3y. So simply we are getting y prime to be equal to 2s over 3y. This may be our last example. You have to go and try your hands on this. Good. So now you see that this is in this form. So we can say that f of a function of s, a function in terms of s and y is what? 2s over 3y. Very good. So check. Is this one continuous everywhere? About the point 0, 0. Now watch. Do the substitution and see what you're going to get. 2, 0, 3, 0. So here we are going to get 0 over what? 0. And you know that 0 over 0 is indeterminate. So when you put it on a calculator, we are going to get something like a masked error or some sentence error and all that, depending on the type of calculator you are using. So this 0, 0, 0 means that this is not, therefore fsy is not continuous. It's not continuous on everywhere. It's not continuous on everywhere. Then let's go for the fact that, please, the fact that it's not continuous everywhere doesn't mean that the partial derivative of f as respect to y will also going to be not continuous everywhere. Check first before you make your conclusion. Alright? Good. Depending on the question. So we have, let's take the derivative by holding what? By holding s constant. So what we have here is like this. 2s, we are holding this a constant. We are holding s a constant. This and this a constant already. So the whole of this is going to be a constant. So this is multiplied by this. Alright, and this is the same as 2s over 3 y negative 1. Alright, so we take the derivative of only this. So this one will repeat. When you take the derivative of this, you get negative, or let's bring it here, negative 1y. Then you subtract 1 from the power, you get negative 2. So here you are going to get negative 2s over 3 y squared. Alright, hope you can see that. You can see that. Very good. So now you check, is this one continuous everywhere? You are still going to get 0 over 0 about the point this. So we still get 0 over 0. Therefore, partial derivative of f as respect to y is not continuous on everywhere. Therefore, we can now conclude that the differential equation, this is not unique. It's not unique. It's not unique about the point 0, 0, or it has no existence about the point 0, 0. Thank you all for your time. That is all for IVP, that is initial value problem and theorem of existence and uniqueness of solution of first order differential equation. See you for another example. Please make sure you try your hands on it, and until then, bye bye.